So good afternoon, everyone. I am Snehanshu, and today, on the behalf of my team, I'll be presenting our work, ConstructNet, Deep Learning Object Detector for Construction Site Surveillance. So this is these are images of typical construction site, and there are few key observations that everybody makes. The construction site machines are huge. They are really large, and there is minimal to no automation in case of surveillance of a construction site. We all of us might know a person who acts as a supervisor in some construction site, and he looks after the laborers and every operation that is going on. So our motivation was to develop and apply deep learning models which will help in the surveillance part of a construction site and the functioning of a construction site. For that, we, as of now, have restricted ourselves to the object detection and tracking of construction site machines. We have used Alberta construction image dataset as our major dataset. We had access to a subset of that dataset consisting of 7,000 plus images spanning across 10 construction machine classes: dozer, excavator, mobile crane, tower crane, the major ones. There are a few observations I would like all of you to notice. There is a visible class imbalance. Excavator appears a lot more on construction sites, and especially in this data set compared to mobile crane or tower cranes. So that is one of the problems that we will be addressing through our model. Secondly, the average size of a bounding box. Basically, in object detection, our aim is to not only classify the object, but also localize it. For localizing, we draw a bounding box across the object. The average size of bounding box of the objects in this data set ranges from medium to large. So there are no small objects as such, which is a daily life observation. For training, validation, and testing, we have a 80-10:10 split. So basically, our aim was to design lightweight object detection pipeline capable of real-time output so that we can deploy it in CCTV, say, or drones, and rely only on architecture and loss functions to handle data imbalance in the data set, so that the model is generalizable, and if we give the access of this model to somebody else, he or she can handcraft the things. Overview of our model: it is a CNN-based single-stage detector. No transformers, no data, no VITs. Just because transformer models are really bulky, and we would have required 100 to 200 MB to store that model, whereas this current model is just 13.58 MB in FP32. If we move to FP16, we could even scale this down. We are using the FCOS architecture, where the detection works on per pixel basis. So you pass me an image, say it is a 416 into 416 image, and I'll take every pixel and classify it. Is this a pixel of interest? Is this not a pixel of interest? If this is a pixel of interest, does it lie inside a bounding box or outside? If it lies inside, which object? Third, we use ghost shuffle convolution with a pan-net structure for feature aggregations. I'll be discussing on this more in coming slides. Fourth, we use dynamic soft label assignment. That is, when I say, is this a pixel of interest or not, we are not relying on any human or any predefined thresholds. It is totally dependent on the model output, the video feed, and it will at that very moment decide whether to classify this as a pixel of interest or not. Lastly, for bounding box regression, we have used complete IO loss. More on this on the next slide. Let us see the components. So basically, for training or as an input, we had a 416 into 416 image that is passed through a stack of convolution layers. This we call as a backbone. The function of convolution layers is to generate feature maps. It will basically extract different feature maps. Then we take 3 different feature maps from different spatial resolutions, and we pass it to the NEC. The function of NEC is feature aggregation. It will take a smaller feature map with smaller spatial resolution, superpose it with a higher spatial resolution using upsampling. And the module that does some mathematical function in between is ghost shuffle operation. Lastly, we generate 4 feature aggregators feature maps, and these are moved to a detection head. We are using a decoupled detection head. This is where the main thing happens. We have 2 small convolution models. One is responsible for classification and labeling, pixel of interest of excavator class. And the next one is responsible just for detecting the bounding box. Okay, this is an excavator. This should be this large. That is the function of the bounding box regression part of the head. This is a detailed architecture for somebody who is interested. As you can see, we take out 3 spatial maps, we upsample it, then there are GS blocks acting. What is a GS convolution? Our aim was to keep the model lightweight, so we cannot just go for plain convolution every time, but we just also cannot just restrict ourselves with depth-wise convolution. So one way out that has been previously discussed, but I did not see any application as in engineering, was use ghost convolution. That is convolution, then half of the channels are convoluted, half of them are depth-wise convoluted, then they are combined, and in the end, there is a shuffle operation. Whatever channels and features that have been generated, you simply shuffle it to reduce any inherent bias of the model. This keeps our model lightweight, and since this is a feature aggregation part, we needed something good and lightweight. So that is all about GS convolution. Now about DSLA and CIOU loss. As I said, I pass you an image. How do you know that which pixel to classify as what? DSLA is better than the static approaches that are being used all over in the industry, like ATSS. ATSS usually requires an anchor box, or it will require some prior information, how large, how small, where. While DSLA does not require this. It's simply, you make a prediction, DSLA has access to the ground truth box, it will compare, it will give you a list of quality attributes. We just take the top K of it and throw the other ones. It also showed improved accuracy. The originally DSLA paper was applied on anchor-based architecture. Ours is an anchor-free architecture. That's why it's a little bit faster and better, more accurate. Coming on to bounding box, if I draw a bounding box like this, and say this is a rough prediction, how do you optimize it? So there are 2 ways of optimizing it. Either you simply start scaling the aspect ratio, or you separately optimize the height and the width. We tried both the approaches. Both these losses are called complete IOU loss and efficient IOU loss. In our case, in the specific data set, for construction machine, we have observed that optimizing for aspect ratio works really good. There is no need of separately optimizing height and width. This makes our model a little bit faster, and also for a specific number of epochs, CIOU produces better MAP. This is the result from the original paper of ACID. Dr. Bojau, he basically tested it with state-of-art models, that time YOLO V3. Just 2 things I would like all of you to notice. The AP calculation is 11-point interpolation. Secondly, it is not very clear that the mean average precision, is it MAP 50, that is for bounding boxes with the IOU threshold just above 50%, or is it a combined for 50 to 99? Because in the current stage, we are using 50 to 99, which is a much more accurate measure compared to MAP. Going on our model, since the dataset was small, we had to get some baseline, and we have to get some model which suits our specifics. We chose the current CNN state-of-the-art YOLO V8 Nano, 3 million size parameter, and with less data and no handcrafted augmentation whatsoever. YOLO uses Mosaic. No handcrafted augmentation. We have achieved, in most cases, achieved per class MAP more, and the overall MAP 50 is at par with the original ACID results for single stage detectors with less data. Our model size is 3.4 million parameters and 13.58 MB for FP32. Now let us discuss some limitations of our model. First, class imbalance. Since we had refrained ourselves from using any augmentations or any, say, generative networks to get more samples, we did not distribute it statistically. We did face the class imbalance in the final stages as well. Mobile crane, tower crane, and dump truck, these were misclassified again and again. However, our performance is better than the existing models by a lot. For many different models I have tested, we got 8%, 9% margin, and for YOLO V8, 6% margin. The tricky case of dozer and excavator. So here you see 2 images. Both of them have this belt over their wheels. The model essentially confuses both of them. And the dozer excavator is having this jaw kind of a thing. That's why it is better classified. Also, in the dataset, excavator instances are 2.5 times more than dozer. So there is a misclassification of dozer at times. Also because the mud that is over the belt of the dozer wheels it confuses the model whether it is part or not. Lastly, small model. No matter what kind of a labeling strategy you use, the parameters mathematically they reduce the complexity, and it will not allow you to make good predictions. Because remember, for DSLA, we want our model to have some prediction at first. One of the way around this can be using different kind of losses and different label assignment strategies such as DSLA and APSs. Before I leave, I would like to suggest the future scope of our work, and will leave the audience with some questions. For data sets like these and construction images, can we really treat this problem as a long tail detection problem? Long tail detection problem is many classes and a skewed distribution. If we treat this as a long tail distribution problem, we can change losses, we can use two-way losses, group softmax. These are just mathematical losses and have not been used much. Can we improve the label assignment strategies for small models? And lastly, is there actually a need of transformer and handcrafted augmentations? So this is something I would leave all of you with. That's all. Thanks a lot. Questions?